thank you for attending my presentation. So we're going to talk about Proxy SG from Blue Coat. But before I dig into the subject, I'll just tell you a bit about who I am and what I'm doing. So I work for Airbus Group Innovation, which is the R&D department of the Airbus Group, which is known for making planes and also security. So we are a small research team. We're about 12, and we mostly work internally, both on avionics and regular IT stuff, and we do security. Some of you may have heard that this talk was supposed to happen in SysCan back in March, where it was cancelled. So before you ask the question, basically the content is exactly the same as it was in SysCan with a few little modifications, but nothing was censored or nothing was removed from the presentation from SysCan. So now a peek under the Blue Coat. So the goal today is to give you an overview of the work we did reverse engineering and analyzing the Proxy SG. We're going to follow the way we actually worked on it. So we will start low level with the file system, storage, and registry, and we go up the layers until we reach application security. So we'll get a look into binaries, then the kernel and OS mechanisms, then a way to dig into the internals, how we did get into the internals, and then we'll see how the global security of the system is handled and conclude about that. So first, what's a Blue Coat Proxy SG? So it's an enterprise proxy, web proxy, which is one of the most deployed in big companies. So if you're working at companies with tens of thousands of people accessing the web, there is quite a good chance that you're going through a Blue Coat Proxy SG. It's mainly used for URL categorization to filter your access to YouTube outside of the lunch break, but it's also able to do way more. People don't know that, but it's also capable of intercepting and re-encoding video streaming. It's also capable of doing a MAPI and SMB proxy. It's very, very, very complex. It has a lot of features. And what's really interesting is that it's running a proprietary OS. It's not as most appliances running on Linux or FreeBSD or whatever. It's actually running their own operating system, which is called SGOS. So why at Airbus Group did we research Proxy SG? Doesn't seem like very obvious. Well, it's actually widely used in the group, so it's the most common way to access the internet from inside. And well, since it's at the edge of between the web and the internal network, it's a very interesting target for malicious actors, because if you can get into a Proxy SG and take over, you can bypass logging, you can, well, maybe compromise it from the internet if you have a really good exploit. You can also probably man-in-the-middle TLS connections, because, well, Blue Coat Proxy SG is also well known for being able to man-in-the-middle TLS connections. Well, it's a very interesting target. And there is no known previous research, public research on the Proxy SG, so we didn't really know if it was secure or not. And if you look at the security built-ins published by Blue Coat, you just have OpenSSL issues and web interface administration bugs. Nothing really interesting. So the goal of the study was really to assess the global security level of the Proxy SG, so we could know if we had to remove them or not. Also to help the IT guys by writing recommendations for secure deployment based on the findings we had, and also be prepared for forensics if we ever know that the Proxy SG was compromised. Knowing about the internals really helps to do a forensics investigation. Then, okay, why should we publish about Proxy SG? Because we could do the research and keep the results internal. Well, we really thought that's the first public information we're publishing here, but definitely not the first research on Proxy SG. I guess some three-letter agencies based in the US, probably some interesting work done on Proxy SG. And so our goal is to foster research and get researchers look into Proxy SG, maybe find bugs and then publish them so they can get fixed. And in the end, Airbus gets a better security from Proxy SG. So today's presentation is going to focus on the raw technical results and also on the way we did it to acquire them. And so, as I said, we were going to go from the low level to the high level, and that's what we did. We also, here everything I'm going to talk about is going to apply to all the current Proxy SG models that are running version 6 up to Q1 2015, because since we started talking with Blue Coat, they made a few changes to the OS and improved security. So I'm going to tell you about the changes, but mostly this applies until, well, last year. So if you want to run a Proxy SG, you have two choices. Either you buy an appliance, which is basically a rackable server running Intel CPUs with off-the-shelf components, HDDs, RAM, nothing very special. Or you can buy a VMware appliance that you put on ESX and run it the other way. Basically, the two are really the same. They're running the same operating systems. There is no difference between the two. It's also very interesting that it's running on commodity hardware, but it's running a proprietary OS, and there is nothing published about it. So I don't know why. The common versions that you can find in the wild are 5.5. It should be over by now, but some older hardware don't support 6, so you may find some 5.5. I'm not going to talk about 5.5, it's really old, and some of the security measures that we have in 6 don't apply to 5.5. The one you're probably going to find in the wild is 6.2, which is the previous long-term release, which is now deprecated, so you should move to 6.5, which is the latest long-term release that Blue Coat recommends running. So we worked on both hardware and VMware appliances. VMware is really easier to work with, but we wanted to make sure that the results that we had also apply to hardware. So first, you want to get a look at the binaries. You want to know what code is running in the Blue Coat. So you have to access the file system. We started with older version of version 6, which is based on a fully proprietary disk partitioning format. So you take the disk of the Blue Coat, you look at it, and you're like, this is not fat, this is nothing I know, the partition scheme is not standard. So you start from nothing. Fortunately, from 6.4, they started to move to a small FAT32 partition that then contains proprietary file system. We'll see that later. So it's easier to start with something like 6.4. So how do we get into the file system? I'll just give you a small introduction on how the hardware works. So the basic architecture is that you have 3 disks, which is, you can have more, but that's the minimum of disks you can have. And so you usually have a small compact flash or SSD, which is used for the operating system itself. And then you have 2 or more drives that are used to store everything else. That's mostly configuration data, and also, of course, the cache file for the proxy and all the user data that is stored in the proprietary file system. So there are 2 types of file systems that you can find in the Blue Coat, besides the FAT32 that is not really used. You have the static read-only file system that is used to store the operating system files. That's called BCFS. And you will find there the binaries and also static configuration put on by Blue Coat regarding the kernel and everything. We'll go back into that later. Then you have the cache engine, which is where the data is stored, mostly the web data, which is based on hash tables. The most complete documentation, if you can call that the legalese that you can find in patents, well, there is the patents that describes the principle of the CEFS, but it's not really easy to read. And you also have, even though it's not really a file system, you also have the registry, which is storing the settings, which is stored into CEFS. And so we don't really know. I tried researching CEFS, but it's really, really complex. And so I don't know how it's stored on disk itself. So we didn't really go into that way of research. It's kind of a shame because the logs are stored in CEFS. So if you want to do forensics and extract the logs, you have to understand CEFS correctly if you don't want to use the interface. But it's so complex, we didn't have the time to dig into it. So today I'm going to present only BCFS, which is the static file system storing the file system files, binaries. So where do you get into BCFS? So if you look at the FAT32 partitions, you have several files. At least, I mean, only 5 of them, and 2 of them, starter.si and system1, are using BCFS. It's very interesting because they actually rewrote bootloader, which is based on their proprietary OS. So when you're starting the bootloader, starter.si, which is a small small for a bootloader, not really, but it's a 6 megabytes binary containing a basic SGOS with a uniprocessor kernel and some drivers, but no applications. Its goal is just to look up on the disk, look for the available systems that you can boot, and then it displays a grub-like boot menu where you can choose which version of the OS you want to start. Once you select it or just let the default start, it boots one of the systems. So by default, you only have one, which is system1, which is the real operating system where you have a file over 200 megabytes, which contains everything, the multiprocessor kernel, the UI, the applications, everything. So to summarize the boot sequence, you boot the BIOS, then the MBR. The MBR checks the boot sector. Then it boots boot.exe, which is found by a hard-coded sector number. The boot.exe starts kernel.exe, which is stored in starter.si, which is the first file entry. We'll see that there. Then it starts sequencer.exe, which is the second entry in starter.si, which is really interesting because it's actually a script parser. And there are a few configuration files in the root of the file system, of the BCFS file system, where you can find, well, the main.cfg script, which is basically the init script, and it will load all the drivers and applications. And then at the end, main.cfg load starters.exe, which displays the boot menu, and then starter.exe loads the selected system. So an interesting boot sequence, which was kind of hard to get to because we had to reverse engineer every step and understand how it came in the end. So I'll just give you an overview of the BCFS file format. I'm not going to explain everything because it's not the goal here. This slide is going to be a reference. If you want to dig into the file system, you will have all the structures. And if you look into an hexadecimal editor and take a look at this, it will make sense immediately. But what's really interesting is if you look at the way it's stored, you have several entries where you have a string table here, a CPIE table, which basically is a table with all the offsets and size for files. So if you want to unpack the file system, which is read-only, you just look for the tables, you match the string names with the offset and size, and then you can extract all the file system. And all the strings contain the full path, so the string you will have boot / SGOS / whatever. So you have the full file system stored linearly in the file itself. The thing is, with this format, you cannot really change the size. If you want to modify the system, you cannot really change the size of the files because they are next to each other in the file content block. So if you want to change the size, you really have to rebuild the whole structure. So we don't really do that. You also have something that you must pay attention to. In the header, you have a CRC until 6.4. And starting from 6.5, you also have a HMAC, which is supposed to guarantee the integrity of the file system. That's it. It's quite kind of easy. Once you understood how it's stored, it's kind of easy to extract the data. You also have something called the CPV, which I will talk about later, right now. So the CPV are the system image configuration variables, which is basically like a kernel boot command line on Linux or the BCD on Windows. It stores the low-level settings for the kernel. So here you have the structure. It's not really interesting. What's really interesting is that you have the variable names, which are referenced actually by section and number. So you don't have the names in the file system itself. But if you look into sequencer.exe, you have all the correspondence between the numbers and the variable names. Unfortunately, I discovered that like when I was writing the slides for the talk. So I just had to reverse and get the meaning from the code and not from the names. Some interesting variables are the section 4 kernel and the 4,0 variables, which is the flags, where you can enable very interesting stuff like a kernel debug log, a GDB stub, ask for an interrupt at startup. You can also change with 4.3 the console speed. So by default it's 9600, so it's very slow. So you can change that and have a faster console. So it's quite useful. So that's one of the things you can find in the BCFS file system, which is read-only. Now I'll say a few words about the CEFS, so the catch engine, which is the writable one. We don't know really about. As I said before, it's a hash table based. It's really interesting because by default you have no guarantee that the files that you store into this file system are going to be permanently here. They can get evicted if there is no space, and if your entry is too old, it would get evicted if you need space. So that's kind of weird because they actually use that file system to store the settings. So you don't want the settings to disappear because you're starting to use all the disk space. So they have some kind of regular files that they have with this prefix. So if you store a file in this file system using this prefix, you will get the guarantee that it's going to be treated like a regular file and not get deleted if the space is going low. So if you just look for legacy cache engine in the binaries, you get a few interesting strings like authorize key, snmp.log, and registry.xml, which is used to store the settings. So the registry is a tree structure, a bit like the Windows registry, except that it's stored on an XML file on the CEFS. And if you look into the code, the entries are referenced by strings separated by columns. So config, column authenticator, column local users will get you all the local users of the proxy SG from the registry. So from the usual web interface, you can get an access to the almost complete registry as long as you have an admin access to the Blue Coat. So if you use these URLs, you can access the registry. Unfortunately, the interface censors some of the entries. So you get like passwords, hashes are censored, and if you want to access them, well, you might want to audit the passwords. Then you have to use the CLI extensions that are here, and I will talk about the CLI extensions later. So to sum it about the storage, you have a FAT32 partition, which contains a static file system called BCFS, which contains all the binaries, the file system for the OS and the web interface and everything. And then you have CEFS, which is the writable storage, which contains the web data and also the registry. So once we manage to extract everything, of course, we dig up into binaries. We wanted to know how the OS runs. So the binaries, you can find them deep into the tree of the file system. That's not really interesting, but in the end you have the stripped directory where you have all the libraries and programs, and you can also find the kernel and drivers. In the root of the file system, as I said before, you have a configuration files that are interpreted by sequencer.exe when you start the system. It's kind of the init system which set up some variables and also starts the binaries. So if you go back into stripped, you have all the binaries. The binaries are ELF files. Everything is in ELF files. So the extensions are kind of weird because they ELF files with .exe, .so, and .so. I guess it's because version 5 was not using ELF, but using PE. I don't know why they changed from PE to ELF, probably some weird reason. So you can either have 32 or 64 bits version of the operating systems. It's mostly depending on the hardware. So if you have a hardware with a small amount of RAM, about 2 gigabytes, then you get a 32 bits. And if you have more than 4 gigabytes, you will get a 64 bits version. We'll see why later. So all the code written by Blue Coat is in C++. Compared with G++ with a custom target. So there is all the binaries taken together amount to between 70 and 80 megabytes. So you can imagine, besides the open source libraries, everything is C++, so you have around 50 or 60 megabytes of C++ code to reverse engineer. So it's terrible. Fortunately, the binaries are not just C++ empty things. You have a lot of unit tests. So every binary, every library integrates unit tests that you can trigger from the web interface. So you can make sure everything works correctly using the unit tests, which is very good for the reverse engineer because there is a lot of debug information in the unit test, debug strings. So you can get insights of what's going on just by looking and running the unit tests. Also, you have a few, well, 2,600 source file names that are referenced in the code, sometimes to display debug strings, sometimes to for backtrace or whatever. So you have also information from the source file names. Unfortunately, everything is stripped, so you don't have the internal names or variables or whatever. But since there are a lot of libraries, a lot of dynamic libraries, you have a lot of external symbols. So for example, libhttp.exe.so has several thousands of exports. So it gives you an idea of what's going on in every function because they are mostly called from external binaries. But they are using C++ and templates, so that's an actual symbol that you can find in the binaries. So when you look at that, you just, I don't want to see that. And of course, to make things even worse, in 32 bits, they are not using the usual ABI where the parameters to functions are passed through the stack. They recompiled probably with mrecpom settings from GCC, which passes the arguments through registers instead of stack, which is very annoying because IDA is then lost. It doesn't know how to track the types of the arguments from function to function. In 64 bits, they're using the standard system ABI. So the first look is really, what am I going to do? Then you look for, of course, open source libraries because you know that people are taking open source libraries because it's less work. So I just took a look and tried to find everything that was available open source. The first thing that was really interesting, the numbers are from 6.5, a bit more than 1 year ago, is their memory allocator they use called bget was published in 72. So I was okay. So it's an open source one. It's actually really good, very simple, but it's kind of surprising. They are mostly using very old versions of the libraries, so I was kind of concerned that they were full of holes. But in conference call, Blue Coat stated that they actually backfork the fixes regularly without necessarily changing the version string. So take their word, I don't know. So some of them are really old, but yeah. So we have the binaries, and then we wanted to know about the kernel and the security mechanisms that you can have. So how does it work? Well, the kernel in practice is very small. It's 800 kilobytes, and it's just handling basic primitives like you would expect from a kernel, like interrupt and exception handling, semaphores, log, message passing through processes, drivers. And as you would do in Windows or Linux with the libc and kernel32.dll, the kernel is not called directly from the binaries. It's abstracted to like a library, libkernel API. So if you want to know what's going on and what syscalls are called, you just reverse engineer the API library. Something really interesting too is the kernel provides at a fixed address a structure, a pointer to a structure, which is kind of like the thread environment block on Windows, which contains the PID, the name of the task, the parent PID, some of the internal stuff that the process might want to know about. So the kernel is very small, but it provides a bit more than 100 syscalls, and it's really nice because in the kernel you have a nice table with the syscall number and next to it the syscall name. So you don't even have to reverse engineer every syscall to get what it's doing. You just look at the name and that's it. So we didn't spend that much time looking at the kernel, but we wanted to know about the way the syscalls are done. So you have two ways to call the kernel, either in 32 bits and 64 bits. They're really the same. You just call a call gate, which is at the fixed address, and you pass a structure pointed by AAX where you have basic stuff. A return code will be stored when you get back from the syscall, and then you have 4 arguments and the syscall number. Nothing really special. Exactly the same for 64 bits, except the address, of course, is different, and the structure is 64 bits variables instead of 32. But that's not the most interesting thing about a kernel. You just guessed that you have syscall and everything. We really wanted to know about the memory organization and the way tasks are separated. Well, that was really surprising. Basically, everything runs in ring 0. everything. So all the tasks, the kernel, everything in the ring 0. So I didn't believe it at first. I was like, okay, we're back to the 90s. That's kind of weird. So I spent really a few days to make sure I wasn't mistaken. And even if you look at the older hardware in 32 bits, you even sometimes have a almost perfect mapping between virtual addresses and physical addresses. So when you access a virtual address, you have a 99% chance you're actually addressing the physical address, which is really, really impressive. So I think it was for performance because they mentioned it in their patent that dates from the 90s, but well. So every task can write everywhere, no protection from anything. Also, the operating system is a bit special. It's not like Windows or Linux. You cannot execute binaries. You cannot load a binary onto the system and run it. You only have one choice, is you put your binary in the read-only BCFS image, and then when the kernel boots, it will load every binary from the image and relocate them. So you only have one choice. If you want to execute something, it has to be first in the image, and it has to register an entry point that is referenced by the kernel that you can call. So basically, everything has to be there at boot if you want to run something, or you have to find a way to execute code, but you cannot just do and put your exe file and run it. So when we did this research, we also wanted a way to get into the internals easily and not have to do everything statically. So we looked into things to make our job easier. So first, we developed a few tools, which we are not going to release, I'm saying it right now, but it's to give you an idea. So a few IDA plugins to just help from the things I said before, rename the syscall automatically, get the function names from the debug logs, get the source file names from the debug logs, and also in the code you can find all the CLI commands that you could type as an administrator that are stored in a very nice structure. And so we wanted to make sure everything was documented. Of course, some of the commands weren't documented, and it's interesting to get them. The most important tool to develop when you're working with a Blue Coat Proxy SG is to have a way to modify the file system very easily. So we developed a Fuse tool to mount the system images with read-write access without enabling size change because it was too complex to implement, and also to change the system variables. And of course, when you unmount the file system, it fixes the CRC and HMAC. So if you want to change something, some code, some variables, some whatever, you just have to mount it, change it, unmount, and then you can boot it into your VMware machine, for example. So some useful tricks also to get more information out of your Proxy SG is to enable debug information. So you need to modify the system image that you're going to boot. So you need either physical access or maybe remote code execution. So you can, if you change the flags for the kernel, you can enable a print K, a debug log. When the system starts, it will output a lot of information about what it's doing. By default, it just tells you nothing. And most importantly, if you change one variable called customer release in maincr.cfg, so if you set customer release to 0, basically you're changing your Proxy SG to a developer mode, which gives you access to a lot of debug commands and information, which is not possible by default. So when you enable the debug mode, you have access to more than 200 CLI extensions. The one that I mentioned to access the registry, for example, and you can have. They allow you to access all the internals of the userland components of the Proxy SG. So you have everything to dump your configuration, show the advanced URL for management, show the state of all the services if you want to see what's listening on what port. By default, you cannot check that, so you might want to enable debug log. And the most important feature is that for almost every component that is running, almost every application, you can enable a very verbose debug log that will get you a lot of internal information. Same for the policy with the policy debug trace on. So once you enable the debug mode, you have access to a lot of information. So that's just an example of the CAG command. And also you can dub the whole registry without the censorship for the passwords using one of those commands. Also, very interesting, the kernel provides a GDB stub. So when you look at the code of the kernel, it's very obvious that there is a GDB stub because you have a string like GDB monitor running. Unfortunately, it's not standard. So I was like, okay, I got GDB enabled. It's telling me at the beginning, okay, GDB monitor starting. And then it took me weeks, maybe 1 or 2, to get into it. Because in theory, you can access it through the COM1 console, but that's the console that is used by the administrator to administrate the proxy SG. So by default, when you type in commands, it's just like you're logging into the proxy SG. So GDB would send commands to the stub, but they would get interpreted by the login prompt or just the interpreter. So I discovered that you have to get an exception so that the GDB stub gets starts listening on COM1, and then you have to send a magic sequence of 2 bytes, 18 and 14, on COM1, and then the kernel starts parsing the commands as GDB commands and not as usual administration commands. So once you've done that, okay, you can send GDB commands, but then they are not using the standard GDB remote protocol, so you have to make sure that either you patch your client or you use a special command to disable the paging, because paging is not handled on the client side as usual, but on the server side. So you would get like the first 80 lines, and then it would stop waiting for a command to continue, and you would have to reboot your proxy SG. So you have GDB, so you can debug. That's really cool. And you also have something really interesting, and that I didn't know about before, is that you can have something called monitor extensions. So GDB can send commands to the kernel. And so if you type, for example, monitor KNL processes, which is the one there, it will send the string to the kernel, and the kernel will give you the result. And so everything is implemented in the kernel. And so you have like 30 commands that you can run, and that will display all the kernel internals. So you have one to display all the active processes. If you want to have the details of one process, you can show the process descriptor using PD. You can also list all the images running on all the health images running on the proxy SG with their address and everything. So you don't even have to reverse engineer the kernel to find out the structures. The commands give you everything. That's nice. So if you want to get for a practical understanding of the proxy SG, one thing you might want to check is the way it parses HTTP requests, because that might be the easiest to access to an attacker. That's the attack surface an attacker would go to, because you just have to do an HTTP request to the proxy SG if you have a vulnerability to get remote code execution. So in practice, if you want to check how it works, well, you just activate the debug log. You make a request through the proxy, you get the log, and fortunately, you get all the function names in the log. So you just have to grep the binaries and look for libhttp.xso and look for the cross-reference for the string, and you got your function. So that's just an extract from the log, and there is this function that is apparently very interesting. If you want to look for vulnerabilities, parse requests seem cool, but then you go into that. So that's the CFG for parse request. The function is around 16 kilobytes. So, and of course it's C++. So when you're like, okay, I really have to dig into this. It's terrible. But then you realize no parsing is actually done by this function. That's just the logic of the parsing, and there are calls to C++ object to do the parsing. So you don't just have to look at 16 kilobytes. You have to look at like 50 or 60 kilobytes of code in C++. So well, and of course it's threaded. It's not just easy to do. So you want to debug and not just do static reverse engineering. So you just look for the image base using the GDB monitor extension. You relocate the binary in IDA, and you set a breakpoint using the CLI in proxy SG, and then you can connect. Unfortunately, stepping doesn't really work, so you have to make sure and put all your breakpoints by hand. I don't know why. So even though you have access to the code, it's not really easy. But well, so I've told you about what we did, and I'm now going to give you a bit of information about the security of the product itself. So first, aware of application security, we the overall goal was to get a global assessment of the security of the Proxy SG, not just the kernel and the internals. So if you check the higher levels, for authentication, for example, by default, local passwords are hashed with FreeBSD MD5. So it's not that bad. It also supports Blowfish. The code is there, but I don't know how to trigger the hashing of passwords using Blowfish. It's too bad. And you have also a way to authenticate with everything that exists on the planet to manage authentication, AD, all the identity management things that you can imagine, Oracle, whatever. Well, authentication is not that bad. Also by default, when you just buy a new box, the only protocols that are enabled are HTTPS and SSH. So you don't have Telnet or plaintext protocol. That's good. Unfortunately, for access control, you have only two types of accounts. So you either have full admin access or you have a read-only account. And you cannot have fine-grained access control to different variables or type of configuration. So read-only is interesting if you want to just monitor the configuration or if you want to give people access to audit or check the configuration. Regarding boot and trust in the operating system, the first interesting thing is updates are signed correctly. So you cannot compromise and backdoor a Proxy SG by doing an update with a backdoor and pushing it. They are checked correctly. The code is okay. Unfortunately, local images, so the ones that are started when you boot, are not really trustable, because before 6.5 it was only a CRC for integrity checks, and from 6.5 they changed and put an HMAC SHA-1. Well, it took me less than 2 hours to get the key, so it wasn't really an efficient protection. I'll talk about that later again. And also, when you want to check application security, you want to check that the crypto is done correctly. Almost everything is based on OpenSSL, and they get the latest version. So OpenSSL is not the best one, maybe, but at least it's not their own custom crypto that they run, and they make sure that they patch it regularly. And everything that is critical regarding to security, regarding random, for example, generating private keys or whatever is needing random securely, is using OpenSSL, and they are using an entropy generator that seems pretty well. So crypto is good. So basically, application security is not that bad, apparently. If you look at the administration interface, you have two different flavors. The new one is the Flash interface. It's nice, and well, it's Flash. But then you get worse. You got the real interface, the one you can do everything with, is, that's the kind of interface you have your special Windows XP VM with iOS 6 and Java 6 plugin that you don't want to connect to the internet. That's the kind of interface we're talking about. So everything is running in Java, and it's a pain in what? But what's really interesting is that both interfaces work by actually posting CLI commands to an URL. So there are just front ends to the CLI. And if you remember, there are two types of accounts. There are read-only accounts and admin accounts. And even for read-only users, they are posting commands to an enable shell. So you're like, read-only, enable, what could possibly go wrong? Actually, they fixed security vulnerabilities a few years ago where it was really easy to do a privilege escalation using this. But then they added restricted commands. So in theory, you shouldn't be able to modify the configuration because they restrict you to a set of commands. But I guess I didn't really look into it, but I guess it can probably go wrong. Also, the Java interface has something really special. They have a RPC mechanism, which is not really interesting, but instead of using the HTTPS connection from the browser, they actually do a new connection using the Java stack and to connect to and post the commands. I don't know why they don't use the one for the browser. So you have two SSL stack that connect to the same thing, that don't have the same security properties. What could possibly go wrong? So just an example. If you want to, when you go to the Java interface, it shows you the version, and it's actually sending this request to the server. and you have the show version command, and then you have the reply there. That is, you don't even have the proxy SG prompt, and you get the command and the result, which is parsed. So interesting. So if we want to summarize about the system level security, what you saw before, well, some bad things first. The code is compiled with GCC, but they didn't enable the stack protector, so no stack canaries. If you have a stack buffer overflow, game over. No ASLR, so game over. Everything in ring 0, game over. Kernel code gate, fixed address, game over. But not everything is bad, actually. You have NX enabled on most platforms, and actually since the latest versions, you have NX enabled everywhere. The big heap from the 70s, they actually have nice asserts, so they compile the asserts in, and you don't have the way to do classical unlink attacks like back in the days with glibc. Actually, if you're running version 5, they don't have the asserts, so if you're running version 5, move to 6.5. Also, well, the read-only file system for binaries, the BCFS, makes it way harder to backdoor the OS, because even if you get remote code execution, if you want to modify one binary, or if you want to make something persistent on the code side, well, you really have to implement your own parser for the file system and make sure you can modify it, patch the CRC or HMAC. So it's not like you can wget a backdoor and run it as a root. It's not really easy. And so basically you need code exec or physical access to change the system image because, well, the updates are signed, so the only way is to modify on the disk. So that's not that bad. And if you want to look specifically into exploitability, what do we have that facilitate exploits? Well, you have the previous slides where ring 0, ASLR, and everything. Of course, it's C++, so you have VTables everywhere. You have function pointers everywhere where you can overwrite and get access to code execution if you have a buffer overflow. And also, it's running C++ code, so it's not like it's running a script language where it's usually safer regarding memory corruption. But then you have some things that are really a pain if you want to run an exploit, because first you're ring 0, so you don't have any protection against memory access or bad memory access, because you can just, for example, bypass NX by changing the PTs or whatever. But then if you fail, well, you reboot the system. So it's kind of obvious. You don't have ASLR, but then remember the binaries are mapped at the beginning of the boot. So it takes all the binaries from the system and maps them into memories continuously. So every version has a different starting address for binaries, because if you change one binary, the size changes, then the position in memory will change. So you don't have a fixed address like in a PE that would get loaded at the 40,000 on Windows. So you would have to have a very precise fingerprint of the Blue Coat Proxy SG to make sure you have the right addresses. But if you have it, then you have no ASLR, so that's it. Of course, then, well, that's obvious, but you have a custom OS, so you're not going to use Metasploit or Metapredator on Proxy SG. You have to write your own custom payload to make a backdoor, add accounts or whatever. So it takes some time. And also, apparently, I didn't see it myself, but Blue Coat told me that they have guard pages somewhere, so it might be a hurdle for exploitation. So, if we want to conclude about the security of the Proxy SG, well, I think what's really interesting is we analyzed a completely unusual and entirely proprietary OS design, which is, even though the security is kind of dated, you feel the design of the 90s, the kernel, the code, and the operating system itself is actually very well designed for what it's meant for, performance and web caching. So they didn't really upgrade it to nowadays security standards, not yet. But it's really good design. The guys know what they're talking about. Also, well, no kernel user isolation or exploit hardening was kind of really unsuspected. The ring 0, I was really surprised. I guess at the beginning, it was really for performance because 20 years ago or maybe 15 years ago, the performance of the hardware was really not as good as today. So they didn't really change and evaluate the impact now. Also, I didn't really look for vulnerabilities per se. I just took a quick look at a few functions, but I didn't find any obvious vuln. So that's not bad. But then if you look at the release notes, every new version, they document a few software restarts. And so if you look into the details, it's like, yeah, so if you send this kind of request, there is a boundary that is not really respected. So you have, well, ring 0 fault reboot. So I guess you can probably find a few exploitable bugs in the code. So, well, recommendations for better security with Proxy SG. They are kind of obvious, but well, use a dedicated VLAN or LAN for administration. But by default, you don't have a way to do that easily, so you really have to dig into the documentation. You don't want to expose your Java stuff to the net. You just really want to monitor the event log, mostly to investigate reboots, because if you get a reboot, a kind of weird reboot on your Proxy SG, it may be well that someone tried to do and run an exploit on it. So you want to check that. Also, since you don't have any secure boot mechanism yet, you want to physically protect your appliances to avoid someone putting backdoor into your OS. And of course, well, use secure passwords. So that's the recommendations. So a new slide that didn't exist in my original presentation that was meant for SciScan is the security enhancement in Proxy SG. So we had quite a few discussions with Blue Coat on what they could do what they can do to improve the security. So they made sure recently that NX support was added in every version of Proxy SG that is supported right now. They also changed one thing that is really interesting is they changed the boot chain in system image validation. So they didn't really change the mechanism, but they publish the hash of every version of Proxy SG they released. So you can check and type a command to have the hash of every system image that is on your Proxy SG and check them against the hashes published by Blue Coat. So it's not a perfect security measure because if someone has remote code execution and a backdoor, they can change the hashes. But if you have an update, they have to keep up with all the updates. So that's not the best, but it's a start. And they are actually working on secure boot right now, and it should be available in a future release. So that's good. And of course, they removed everything that was debug related. So you don't have any GDB stuff or CLI commands anymore in the latest version. So if you want to research Proxy SG, I really recommend you to go into the older image versions where you still have the debug information and GDB support. And we are still discussing with Blue Coat, and they really consider implementing the separation between user and supervisor, user kernel separation, because their kernel actually supports that. It's just a configuration variable they have to change at compile time. So they just have to recompile with ring 0, ring 3 separation and make sure the performance is still good with the current hardware. So I really hope they are going to do that soon. Well, that concludes the talk. Thank you very much for attending, and if you have any question, I'd be happy to answer. Yep.
How long did it take you to analyze it?
Oh yeah, so how long did it take me? I forgot to say. So a bit more than 2 months full time. But Stéphane Duverger, one of my colleagues, did actually work on the file system a few years before. So I think if we take everything into account, it's probably like 3 months full time. So kind of long, but not too long. Another question, yeah?
You said that the Java does its own SSL stack to do HTTPS.
Yes.
Did you try to man in the middle of that and check if it verifies simplicity?
I didn't really have the time to check that.
Seems like obvious.
You might want to check, yeah.
I don't have that in mind.
Oh yes, that's, well, one of the things Blue Coat told me when at first I was like, yeah, but you have access to Blue Coat, it's not really easy to get one. $200 on eBay. Okay, it's an old one, it's a small one, but you get the code. And at some point you could Google for the right string and get access to a public FTP server where you had a few images with very recent versions. They kind of deleted them since, but don't know why. But yeah, no, getting access to a Blue Coat is not really hard if you, and well, you can get access to some appliances if you know people. It's quite easy. Any other question? Yep.
There's also some ways to feed data into code. We can look at that factory.
To feed data? I didn't really try feeding. Did mostly reverse engineering to get an overview of everything, but we didn't try fuzzing or looking for stuff. So, any other question? Well, thank you very much.